greeting to all. At the outset, I welcome you all who have joined me. Now, COVID pandemic, my salutations and sincere thanks to all for facilitating the learning process without interruption. I welcome Dr. Raj, Principal National College of Tiruchirappalli, a dynamic personality who is the president
is not visible.
No, please click to the Ramasamy Jayavel the folder, then you will be able to get it, because others are able to see the slides. Okay. Okay, then we are, so from third generation, then we move to fourth generation nanostructures, which are all typically molecular nanosystems. And these molecular nanosystems are, very tiny structures where we move from even close to molecular level or atomic scale. And so those kind of molecular nanostructures are now very efficiently prepared in the laboratory. And you know that recently there was a demonstration that these molecular assemblies can also form a molecular machine. And that concept was developed in 2015. And they got the Nobel Prize in Chemistry in 2016. So since then, semiconductors like silicon and germanium. So in order to make it P-type or N-type, then we have different kinds of doping like phosphorus, boron, this kind of thing. But the uniqueness of these structures, so even without any external doping or without any external force acting on these materials, the energy gap can be tuned by simply increasing the size of this particle. But in the case of cadmium selenide, for example, if you increase the size from 2.8 nanometer to 4.2 nanometer, there is a progressive decrease in the energy gap value. It goes from 2.5 electron volt to 2.2 electron volt. Because the reason was that those who are very familiar with the electronic states or energy states of these different kinds of material, and the quantum dot structures will have a very discrete level. And if you take a valency band and conduction band, in between we have different discrete levels. And if you optimize the conditions and bring down the size to less than Bohr exciton radius, and each and every discrete level becomes more stable. So therefore, you have the intermediate levels. Then the distance between that intermediate level is considered as your lower energy level, and the difference becomes very low. So that is what if you increase the size, then the increase the energy gap values. And even though the size of these particles are very, very tiny, you have plenty of application possibilities using these quantum dots. Okay, so these quantum dots are useful for sensing applications, or we can do the photo degradation, or we can also do the bioimaging, and it's also useful for the diagnostic applications or therapeutic applications, drug delivery, and solar cells. We have a lot of application aspects for this kind of materials. And in fact, in our laboratory, we have been extensively working on quantum dots to make quantum dot synthesis solar cells. And we have also made heterojunction solar cells. We can use it for hydrogen production. And we can also demonstrate the sensor applications where these tiny materials can be useful for DNA hybridization sensing, or we can also use it for So these are all some of the applications where we can use these quantum dot structures. And the second category is the one-dimensional nanostructures. This is also very familiar structures, and many of you are aware, and I'm sure that some of you are already working on this material. And this was discovered in 1993 by the Japanese professor Ijima. And the speciality of this structure is that we can achieve the surface area of very close to 1,000 meters squared per gram for this kind of single wall carbon nanotubes. Okay, the diameter of these typical nanotubes is about 1 to 2 nanometer. Okay, for example, if you prepare 1 gram of material, the area available for application is almost 1 square kilometer. So that is the interesting phenomenon of these materials, and these materials are also extensively studied for variety of applications. And especially for this one-dimensional structures, we'll have two different configurations. One is about single-wall carbon nanotubes, and this is multi-wall cascade structures. These kind of structures again have the surface area of about 200 meters squared per gram, and the diameter for this kind of multi-wall carbon nanotube goes almost 20 nanometer plus. Okay, so these materials are also again useful for variety of applications. When you talk about one-dimensional nanostructures, there are one-dimensional nanotubes, and these are all nanowires, or these are all nano structures like carbon nanotube. And for example, if you take the carbon nanotube, And now there are a lot of interesting applications to replace this carbon silicon technology with carbon nanotubes. So if you use the silicon technology, the silicon wires useful for the electrical leads is about 50 nanometer. So if you are able to replace this silicon with carbon nanotube, you can just see the size is almost 25 times reduction. So already silicon technology is the miniaturized technology. So the use of carbon nanotubes is called what is called ultra miniaturized technology, especially in electronics. And coming to the mechanical strength of this material, we know the high strength steel alloy. It is called as 316 alloy, which is useful for all construction purposes. And the mechanical strength of this high strength steel alloy is about 2 billion Pascal, whereas the carbon nanotubes can have almost 25 times stronger than high strength steel alloy. Because this is because of the reason that we have the carbon nanotubes made up of carbon-carbon bonding, and the carbon-carbon bonding is the strongest known bond in nature. So therefore, these materials exhibit such a very high mechanical strength. So not only the mechanical strength, if you look into the current carrying capacity or the conductivity for the conventional copper wire, which is useful for the transmission purpose, where the conductivity is of the order of 10 power 6 ampere per centimeter square, whereas the carbon nanotubes can have almost 3 orders of higher conductivity. It goes to 10 power 9 ampere per centimeter square. So in order to realize all these interesting applications, what we need is the high quality material. Okay, so today the high quality electronic grade carbon nanotubes cost about $100 per gram, which is almost twice that of the gold cost today. In fact, in few years back, this was almost 3 or 4 times. But at the instant days that the carbon nanotube production has become commercial, that we have competitive price. But unfortunately, the gold price is going up. So it is now at stands at 2 times that of the gold cost. But in future, it will be even less than the gold cost. But there are a lot of techniques which are all developed to have this kind of carbon nanotubes prepared in affordable cost, so that any of these applications can be realized for practical usage. So these are all 3 different forms of nanostructures, which are all one-dimensional with very high aspect ratio. And these are all some of the demonstrations, the transistors fabricated with these carbon nanotubes, and these also different kinds of vertical structures, because now the vertical gate structure is become very famous, so that we can have the large-scale integration of these electric circuits. And we can also use this kind of carbon nanotubes as a linker between the source, gate, and drain through a dielectric medium. And not only for these electronic applications, we can also make these carbon nanotubes with very complicated structures to fabricate sensors. These kind of structures are called MESA structures, which are all very, very tiny and very sensitive. And it has got a lot of interesting applications. And so carbon nanotubes is a very important source for CO2 capture. Okay, so this kind of anodes are fabricated from these carbon nanofibers or carbon nanotubes, which can be used for CO2 capture from atmosphere, as well as this kind of industrial processing. So then the third category is about the 2-dimensional nanostructures. And the 2D nanostructure has a very unique property where these materials can be prepared in a very, very ultra small size.
Hello.
Atomic. Yes. Yes, is okay. Shall I proceed?
Okay, sir. Okay, sir. Proceed, sir.
So these structures have a very unique property where we can prepare the structures in a single atomic layer structures. And because these are all typically layered structures, and if you optimize the properties, we will be able to isolate these kind of structures in a very, very controlled manner. And these structures will have a lot of interesting applications. And there are a lot of interesting story behind these materials, because we have different kinds of sulfides, nitrides, oxides, which are all typically one-dimensional, 2-dimensional structures. So the very well-known example for 2-dimensional structure is graphene, and we also have hexagonal boron nitride, molybdenum disulfide, tungsten diselenide, And it's also possible that we can fluorinate this graphene to get what is called fluorinated graphene or fluorographene. So like that, we can make these two kind of materials combined together to form different heterostructures, and that was also possible. So the interesting phenomena is that the synthesis itself is very tricky process, because we have to isolate the atomic layers without any damage, because it's all very highly flexible also. And people do a lot of modeling to optimize the process so that this can be prepared. And once we prepare the material, then we do the characterization and then look for applications. That's what the protocol goes. And if you take generally the 2D materials given in this slide, and those materials will have different kinds of properties. For example, hexagonal boron nitride is highly insulating with the energy gap of more than 5 electron volt. And molybdenum sulfide and tungsten selenide, these are all basically typical semiconductor structures with the energy gap value between 1 to 2 electron volt. And there some materials are half metals, some of them are semi-metals like graphene, which is actually a zero band gap material. And some of them is highly metallic, like vanadium oxide and vanadium sulfide. And some materials will have extreme conductivity, and those materials are called superconductors. Okay, so there are a lot of interesting phenomena in these materials, because when we talk about even a bulk materials, the defect plays a very major role in determining the functionalities and properties of this material. But when we deal with the single atomic layer, obviously the defect influence will be very high. So the defect engineering itself is a very important area where people are working on that. And when we make this kind of heterostructures, and the interface between these two layers is also very important, and there should be a perfect matching between the two layers, so that the interface becomes more stable and useful for applications. So the interface engineering is also another area. And in general, the structural engineering itself is a major challenge. So there are a lot of interesting applications happening with this. So with this background, so the applications of these 2D materials is very enormous. As I said, the 2D materials are multifunctional materials where we can use it for communication applications, digital analog circuits. This can also be useful for interconnects, memory applications, and sensors. And because of the flexibility, there are a lot of flexible devices like wearable touch sensors, or the flexible touch sensors, or the transparent conductors, or biological applications like antibacterial, antiviral, or tribological applications. Or it can also be integrated with the large scale structures like concrete, reinforced with the 2D materials to increase the strength and also durability of this kind of materials. In the case of electronic applications, again, like one-dimensional nanostructures, 2D materials are also useful for a variety of applications, including ultra large scale integration devices or extremely large scale integration devices, because these structures can be useful for realizing the extremely large scale integration devices where millions and millions of transistors can be integrated in a single chip. So when we talk about the extremely large scale integration devices, it doesn't mean that you fabricate 1 million transistors separately and then try to integrate this. That was not possible. So what they do is that they will just make this kind of 2D layers, and each and every electron can perform a transistor action. So if you just make these electrons to perform a transistor action, it was possible that we can integrate 1 million electrons together. So that it means you have 1 million transistors integrated for the extremely large scale devices. So those kind of devices are called single electron devices, or the transistor based on single electrons are called the single electron transistors. So similar to one-dimensional carbon nanotubes, these 2D materials are so useful for diagnostic applications, therapeutic applications, sensing, bioimaging, and it's also useful to some extent for biotech safety applications. And LED is another interesting applications which has now come from the commercial stage, and a lot of LEDs are fabricated using these 2D layered materials. And because of the variation in the energy gap, as I introduced already, and it goes from 6 electron volt to almost 0 electron volt. And this kind of variation is responsible for the absorption to the entire range of electromagnetic spectrum, starting from UV to visible, visible to near IR, far IR, terahertz or microwave frequencies. So, okay, because of this properties, there are a lot of interesting applications in photonics. And as I said, today I will be just discussing some of the techniques which are all available for the synthesis of this material. And so I'll just start with the slide where we just classify the synthesis of nanostructures in two different categories. One is the top-down approach where we just deal with the bulk materials. If you assume that this is supposed to be a 3D material, then we convert them to two-dimensional thin films, and this is then converted into one-dimensional wires, and this is taken to zero-dimensional quantum dots. So if you move from the 3D to 2D, 2D to 1D, 1D to zero dimension, that is called a top-down approach. And the best example is that you are all very familiar with the structure, which is there in Mahabalipuram. This is basically a single rock sculptured structure. So that if you consider that a single rock is the bulk, then whatever the structures made up of this sculpture are either one-dimensional or two-dimensional or zero-dimensional like that. And another approach is that starting from atoms to molecules, molecules to one-dimensional structures, one-dimensional to 2D, 2D to 3D. So this classification is called the bottom-up approach, where we build from bottom to achieve these bulk nanostructures. And the typical example is about the Kudumpinar, where this is made up of brick by brick structure to build this massive structure. So these are the two major category of synthesis methods. Under each category, there are plenty of techniques available. So we have to choose based on our requirement, based on the application, what for we are making this material, and also other thing is that based on the infrastructure available in your laboratory. Okay. So generally, when we talk about the classification, there are three major classifications. One is based on the scientific principles. Another one is the raw materials available for the synthesis. And the third classification is about the application aspects. For example, we know that we can do the physical approach or chemical approach. Sometimes we can have a combination of these two physical chemical approaches. And these approaches are classified under scientific principles. And the second approach is about the source materials available. For example, if you wanted to prepare titanium oxide nanoparticles, so we have the titanium oxide inorganic powders, or we can have titanium chloride solution, or we can also have titanium butoxide organometallic form. So whatever is the raw material available in your laboratory or in your stores, then you can choose the appropriate method to synthesize this material. That is the methodology based on the source material. And the third application is about the process technologies or the application aspect. For example, if you wanted to use it for solar cell applications, then we always go for two-dimensional coatings. And if you wanted to use it for energy storage applications, then you can use one-dimensional or three-dimensional nanostructures. So for that case, we have to adopt a different methodology. So this is the major classification. Under each classification, there are plenty of techniques available. I'll just introduce the materials which are available under the classification of scientific principles. As I said, when you talk about the physical approach, the material is physically converted from bulk form, whether it's a micron size or millimeter size or few hundred nano size, then that is converted into the typical nano form, whether it is a two-dimensional or three-dimensional. So that category is called the physical approaches, which includes mechanical milling or mechanical processing, or thermal evaporation followed by condensation, and sputtering, different kinds of sputtering like DC sputtering, RF sputtering, magnetron sputtering. And there is a special technique called the sparkling discharge. And it's also possible that we can do the conventional sintering with the explosive with applying high voltage or high temperature triggering, where we can get these kind of nanostructures. So those kind of techniques are called physical approaches. And comes under the chemical approach, we have the very well-known chemical vapor deposition technique, where we take the materials in a reactor and then heat it, the material at high temperature. Then the chemical reaction decomposes the material to fragments, and then it is converted into vapor, and then vapor is transformed to solid by sublimation process. Then we have the preparation of nanostructures. Under the chemical approaches, we have another technique called precipitation. This is co-precipitation or hydraulic precipitation. You just take the solute in a solvent and then try to optimize the conditions. You get the precipitate at the bottom of the container, and this precipitate can be very controlled, where we can prepare materials of the order of 50 nanometer to 100 nanometer typically. And we can also do the synthesis with a very slightly elevated temperature and pressure, which is called hydrothermal method or solvothermal method. And if you use hydrothermal or solvothermal, then we get the nanomaterials. So if you use water as the solvent, then it becomes hydrothermal, or if you use any organic solution, the solvent, then it becomes solvothermal. And once we prepare this material, we can do the spray coating to make a two-dimensional structures by chemical approach, or we can also do the sol gel synthesis. The sol gel is probably one of the very convenient ways or very inexpensive way of making nanostructures, and this sol gel method is widely used, and so that what you need is a high purity chemicals, and you don't need very much sophistication in the experimental aspects, and so we can simply make this bulk nanostructures, three-dimensional nanostructures, or it is also occasionally prepared the one-dimensional nanostructures using the sol gel method. And conventionally, when we make CVD, the process will be, the reaction will be very slow. In order to enhance the chemical reaction, we can just apply the electric field, so therefore it becomes electrochemical deposition. So these are all some of the techniques available under the chemical approach. And some cases that we combine these two processes, the both physical as well as the chemical approach. For example, if you take CVD, in order to enhance the reaction, then we apply a high energy laser beam, and which is called laser assisted CVD. Or it's also possible that when we hit with high energy lasers, the plasmas are produced, and then plasma enhances the movement of ion atoms towards the substrate, so which is called the plasma enhancer CVD. And these are all some combined technique or conjunctional approaches. And there are some special approaches like bio-inspired approach, especially to prepare biomolecules as a template. Or we can also use high energy laser beams like gamma rays, X-rays, or electron beams to induce the nanostructures in a bulk material. So these are all basically the scientific principles where we have the physical approach as well as the chemical approach. And the second classification is, as I said, classification based on the raw material available. The materials available in three different forms, solution phase, solid phase, and the vapor phase. So if you have raw materials in the solution form, obviously we can go for hydrothermal or solvothermal synthesis, or we can go for electrodeposition or epitaxial layer growth, or we can also use the sol gel method to synthesize the nanostructures. So the second and third category is that if you have a solid material as a raw material, then we can go for strain-induced self-assembly process to make quantum dots, or we can also use what is called diffusion-induced intermediate layers. This is applicable especially for when you make multi-layer structures, and for some reasons, if you wanted to fine-tune the intermediate layer thickness, or you wanted to segment it further for the specific stability, and we can do this diffusion-induced intermediate layer, especially applicable for thin film structures. And in order to make nano composites, we follow different kinds of methods. One is very hot pressing technique, where you just heat it and just press it to make the layered structures, and these layers are typically can be controlled of the order of less than 100 nanometer thickness. And it's also possible, as I said, the reaction sintering. This normal sintering is, for example, if you take heat, that heat energy is absorbed material in a very slow manner. So in order to enhance this one, we can use it in a chemical environment, so that the chemical reaction induces the heat flow in a faster way, where we can achieve the growth in a very faster time. Then we also have micro sintering. Micro sintering is also a very efficient way of making nanocomposites. The reason was, as I said, if you do the conventional sintering, either resistive heating or induction heating, the heat energy is absorbed material on the surface, and it has to diffuse, literally diffuse through the bulk. And this kind of diffusion induces a lot of strain for the lattice. And for high temperature material, if the lattice strain increases to beyond certain limit, then those kind of materials are not useful for any applications. But whereas if you go by microwave sintering, the microwave energy is absorbed by the material either through ionic rotation or dipole moment, because the frequency is very high, microwave frequency. So because of this, there is an instant heating of the material without any lattice strain. So that is the advantage of going for microwave sintering. And of course, I have some slides to demonstrate those things also. So these are all actually the solution-based and solid-based approaches. And if your material in the vapor phase, then we can go by physical vapor deposition. Physical vapor deposition is physically transform the material from one place to another place, and they get deposited over the substrate in the form of nanostructures. And the well-known example is thermal evaporation. This is the most popular method, low cost, pure products. And what you need is a very small vacuum chamber to just evaporate the material at high temperature, and the temperature can be fixed based on the melting point of the material. And we can also use the electron beam for the localized heating, so that small area can be very highly homogeneous. Then we can use it for this electron beam, but it is very, very limited use because it is very localized approach, where then it can work with a very small range of area. And sputtering, as I said, there are different kinds of sputtering. Sputtering is basically, again, taking the material and heat it, and this just evaporates or the fragments the material to small fragments, and these fragments are very controlled, so that it can be completely allowed to, made to deposit on a substrate. And these kind of structures, sputtering is in different forms. One is the magnetron sputtering, or we can have DC sputtering or RF sputtering. Okay, for example, DC and RF sputtering can be useful for metallic coatings, and magnetron sputtering is essential for metal oxide coatings. And there is another physical vapor deposition technique called cathode arc discharge. And this is useful mostly to make carbon nanofibers, one-dimensional nanostructures. And there is yet another method called PLD, pulsed laser deposition technique. This is a very versatile method, especially when we wanted to synthesize materials at high temperatures, because this induces high energy laser pulses, which can go up to 1500 to 1600 degrees Celsius. And as I said, this will be useful for high melting point material. So this is physical approach. Then the second category of vapor phase approach is about the chemical approach, or chemical vapor deposition. So chemical vapor deposition is there are a variety of techniques available under this category. One is the conventional thermal CVD, where we take a small reactor and heat it, and then we can induce the deposition. You can also have the low pressure CVD, so that the some of the material, complex material, which is prepared in ternary or quaternary phases, can be conveniently prepared by low pressure CVD. We can have the plasma enhanced CVD also to enhance the chemical reaction, or we can have a photochemical or laser assisted CVD. And there are some sophisticated technique where we use metallo-organic CVD, metallo-organic chemical vapor deposition. So this technique, especially because the name itself implies that we have to have the metallo-organic form of raw materials. Okay, so we can also have the molecular beam effects, where the material is heated and the molecules are transformed as a beam, and then it gets deposited over the substrate, and we can make epitaxial layers out of that. And the atomic layer deposition is the most advanced technology, where we can control the deposition to go by layer by the addition of individual atoms. So when we have those kind of sophistication, it was possible that we can make a very high quality deposition, and of course it can the defects can also be very considerably decreased in this kind of atomic layer deposition. So advantage of going for this CVD process in general, it is possible that we can have a epitaxial alignment on the substrate, and then uniform dimensionality can be achieved to even go for large scale deposition, and a very good crystallinity can be maintained for this kind of sophisticated process. But obviously, when we have the very high sophistication, then we have to work with high temperatures. And for example, the MOCVD operates at 1400 degrees Celsius. Even MBE, we can go even 1500 degrees Celsius also. So the cost involved in this kind of instrumentation is very exorbitant. And then because there is a restriction, because right, we are dealing with the high temperature and also high vacuum pressure. And if you go for large area, then the investment becomes very huge. So therefore, most of the time, the laboratory scale, small scale deposition is done at the laboratory scale, and only for the industrial scale processing, they go for high area deposition. And the another limitation is that this needs very specific substrates. Generally, the solid substrate, and the substrate would be of a single crystal nature, and to have the very perfect lattice mismatch with the substrate and the deposit nanostructures. Okay, and the CVD is basically very suitable materials, especially for super lattice structures. We can also make the core cell nanostructure fabrications using the CVD process. So these are the major classifications. Under each category, there are plenty of techniques available. Obviously, we cannot have all these techniques discussed in this lecture. And what I just do is I'll just give one or two examples under each category. So this is actually, let us again start with zero-dimensional quantum dots, and this is colloidal synthesis of quantum dot structures. And this is the very easiest way of making quantum dots. What we take is take the material and a proper solvent and dissolve the solvent, and you form the precursor, and precursor has to be mixed with the surfactants. And the role of surfactant is that we are talking about the very, very tiny particles, which is less than the Bohr exciton radius. So because these are all done in a self-assembly process, and once when it reaches the critical stage, then the surfactants that will encapsulate the size, so that there will not be any further growth of these particles beyond its limit of Bohr exciton radius. So if it grows further, then it becomes what is called bulk material. It is no longer the zero-dimensional structures. So we just take the precursor with the surfactants, and then we just optimize the conditions where the monomers are formed. And then these monomers can be just converted into the clusters through nucleation concept. And once the nucleation is induced, then it grows in a critical size, then it forms a nanocrystal. And these nanocrystals, depending upon the size, as I said earlier slide, that it can absorb different wavelengths. And because of the variation in the absorption of the different wavelengths, we have a different color of these nanoparticles. And this is by simply varying the size of the particle. And the colloidal synthesis has a very simple experimental apparatus where we have a 3-neck glass chamber, and this is heated with a heater, so that we have the very uniformity, homogeneity inside the chamber. And you just allow the cold water to hot water, so that we have maintained the temperature properly. Then you have the evaporation is just induced at this stage, so that we have the nucleation started at the bottom, and then it grows to the level. And once it grows, then we have the surfactant which is acting on the material to control the size. So the self-assembly process by colloidal synthesis follows this mechanism, where we can have binary materials like that, or we can also have ternary or quaternary compounds, and it involves a very, very well-ordered structures by self-assembly process. This is the typical quantum dot structures. So when we do this kind of quantum dots, we have to properly optimize the conditions. Otherwise, what will happen is that the nucleation of the clusters, and it try to form the aggregated layers, And if we just control the process in such a way that each layer has become a quantum dot size, then we have the encapsulation is done with this kind of encapsulants. Then we can control the size. And if it is just allowed further, then it can form a bulk crystal like this. Then we can have this kind of formation. So we have to very carefully optimize the conditions. Then we end up with only this kind of structures. So there is a video just to show how this self-assembling happenings on the surface, and you have a very uniform movement of atoms towards the layer which is already formed, and you get this kind of atoms arranged in a very well ordered manner. And if at all any impurities, that impurities are visible, and those kind of areas can be very clearly controlled in this. So this is the very simplest way of making zero-dimensional quantum dots. There is yet another technique called the surface patterning. And this surface patterning is a very unique technique where we can just, instead of using any chemicals or something, we can just take a solid surface, and then you use the atomic force microscope as the cantilever, and then you can just take the material. Because I hope that many of you know about the AFM functioning, because AFM, what it is, you take a solid surface and then you apply a small voltage across this AFM tip, and this is the tip is made up of metallic material, and once you apply the voltage, then there is electrostatic force acting on the tip of this cantilever, and then on the material you have the atomic force acting on this. And when this cantilever is closely moved on the surface, or it touches the surface, there is a synchronize between the atomic force and the electrostatic force acting on this material, cantilever. Then it is used just to probe the surface, and then the probing captures the images. Then the image is converted into a digital image for the observation. So this is the mechanism. And if you take some materials like ferroelectric or ferromagnetic materials, and these materials will have a very tiny domains. Okay, and these domains are called, in the case of ferroelectric, the domains are distinguished in terms of its polarization axis, or in the case of ferromagnetics, the domains are distinguished in terms of its magnetic moment. Okay, so these kind of materials can be like a mechanism. And if you take some materials like ferroelectric or ferromagnetic materials, and these materials will have a very tiny domains. Okay, and these domains are called, in the case of ferroelectric, the domains are distinguished in terms of its polarization axis, or in the case of ferromagnetics, the domains are distinguished in terms of its magnetic moment. Okay, so these kind of what had happened?
This is one of the important loss function. It's kind of, this loss function is very nicely behaved loss function, like a mean squared error loss function, square loss function, and you can the 12 standard students will be able to see it and say that yeah, this is a very nicely behaved loss function. Derivative is defined at each.
Hello, Dr. Pari, something is interrupting.
Sorry, sir. Now it is okay. Please continue, sir.
Okay. So this is actually a very specific technique where we can use the ferroelectric or ferromagnetic material and to make the surface patterning like this. And this kind of dots are called a domain dot. And if we control the applied voltage, where we can confine this in a very small dimension, where we can have this kind of domain patterns. Or if you just reverse the applied voltage, then we can also have this kind of quantum well structures on the surface. And if you just have the AFM tip hitting on the surface in a very uniform manner, then we can have this kind of templates. And these are all useful for micro electromechanical systems, or we can also have these materials for as a template to grow one-dimensional nanostructures. Okay. So this is about the typical method where we can do the surface patterning using this AFM tip, and so this is also useful for template applications. Then the second technique is about the one-dimensional nanostructures, and the one-dimensional structure typical example is the carbon nanotube. And this carbon nanotube is known for many years, and people started using this arc discharge was the very pioneering method to prepare the carbon nanotubes. And this was actually used for the fullerene synthesis, where we take the graphite rods and just ignite at the tip. Then you have the ignition, and then it burn into shoots or plumes, and these shoots are collected, and mostly majority it will be fullerene structures, whether carbon C60 or C70, and sometimes this also gives molecular structure as a one-dimensional structures, which is called carbon nanotubes. But in the arc discharge, the yield was very, very poor. So the people started moving with better technique. Then they started using the laser ablation. They take the carbon or graphite target and hit with high energy laser beams, and you have the fragmentation taking place, and then it moves towards the collector. Then you have the formation of one-dimensional nanotubes deposited on the collector surface. And this is also very uncontrolled manner, where you just hit with the laser beam. And so the improved version of this laser ablation is the CVD process, where we control the temperature along the length of this reactor, because this is actually the 5-zone resistive heating furnace. Then you have the carbon source coming here, and this is the substrate. And then you can just have the any kind of substrate depending upon the operating temperature of the reactor. Then you have the one-dimensional nanostructures grown from the surface using the source which is coming from the other side. Of course, there is some peripheral devices attached with this to control the temperature, vacuum, and other things. And this is the typical CVD reactor. And this is the most optimized technique now. There are a lot of synthesis or industrial scale synthesis process using the CVD. And the typical reaction temperature is around 700 to 900 degrees Celsius. And any of the carbon source like acetylene, ethylene, or benzene can be used, whichever is available in our laboratory. And any kind of inert atmosphere, nitrogen, helium, or argon can be used. And conveniently, we can have conventionally 3-zone horizontal furnace. And very specific requirements, we have to go for 5-zone furnace also. And we can use any of the metallic catalysts like cobalt, iron, nickel, palladium, platinum to enhance the reaction in the CVD process. And there are some templated materials can also be used for them. So this is also not a very sophisticated technique, and you can very fabricate the furnace. It can go up to 1000 degrees Celsius. And only the thing is, like, we have to have this kind of carbon source available in our laboratory, so that the CVD process can be used to make the carbon nanotubes. And this is actually the templated growth. As I said, this kind of nanotubes or dots can be used to make one-dimensional nanostructures grow in a vertical direction. And this is actually a fabricated surface with 1 micron size, where you can have different kinds of domains, which is either positive domain or negative domain. And if you make it a negative domain and just use it as a template to induce the nucleation at these points, then you have a very uniform growth of these nanotubes like this. And this
Hello, sir.
Basically, yes.
Sir, PPT is not visible, sir.
But I think you have to check with your things. You just
No, sir. No, sir. It is visible, sir. You can continue, sir, please.
For others,
Yes,
it's
sir.
visible. You just click
No, we have.
then
Yes.
you will get it. Okay, so this is actually one-dimensional nanostructure. This is a PZT, well-known piezoelectric material, lead zirconate titanate, grown on bismuth titanate template. And you can just see the length goes to almost 100 to 200 micrometer with the wall thickness of 20 to 30 nanometer. Very highly uniform nanostructures can be fabricated with templated growth. Then there is yet another technique which is called the electrospinning technique to make these one-dimensional nanostructures. And the electrospinning technique is also very simple in the case that we take a metallic syringe, what we do, the medical syringe, and this metallic syringe is connected with a high voltage from there. And normally, if you take a medical syringe, then if you just take any liquid or drug in that, if you just press it, when it comes out of the nozzle, it tries to form the droplets. And that is because of the surface tension. But here what we do is we just apply a high voltage across this metallic syringe, so that there is a very strong electrostatic force acting on the tip of this metallic syringe. Then because of this electrostatic force which surpasses the surface tension, so that the liquid coming out of this syringe becomes a molecular network like this. And this molecular network can be prepared as a bulk nanostructures like this, or if we control optimize the process, that you will get only one molecular network coming like this, and which can be formed as a nanotube. And actually there are a lot of parameters to be optimized here, that applied potential across the tip, and of course the other end is connected to the metallic collector here, and the rate at which the solution is coming out of the nozzle, and the tip of this syringe, and also the distance between the nozzle and the collector. These are all the parameters to be optimized. And the typical electrospinning system looks like this, and this cost is about 4 to 5 lakh, because the major cost is about the high voltage source. Okay, this is actually the zinc oxide nano rods which are fabricated by the electrospinning process. And if you just look into the individual rod, then it will have a very high control of this diameter over the very long length. Okay, so this video shows how that you have the molecular beams which coming out of this nozzle, and it goes towards the collector. Then this is the cylindrical collector. It continuously collects these powders when fibers, and then you can, after experiment is over, you can just take out. Then this is actually the metallic foil over which the one-dimensional nanostructure forms. Okay. So this is also very easy way that you can make this kind of one-dimensional nanostructures. Okay, so then let us move on to the 2D nanostructures, because we are running out of time. We have another 15 minutes. So the 2D nanostructures are very well known for many decades, but the recent development is that nanoscale device fabrication using these 2D nanolayers is pushing the technology to the ultimate limit. Okay, so the recent trend is like, when we have the deposition done on a very large scale, it will be useful for a variety of applications. When we go for large scales, then the particle confinement within nano dimension is very, very challenging. And of course, we have to have the very low process temperature, because even 100-degree variation in the temperature also matters a lot. So we have to have the technology to have the very low temperature processing. So when we do the large scale deposition and control the particle size, we have to also improve the uniformity of the material, so that it can be useful for high-end application. And another interesting parameter is about the process damage, reduced process damage. It should have a tolerance. For example, if you make a large area and if you try to fabricate multiple devices, and if something goes wrong somewhere, then the entire structure has to be thrown away, right? So therefore, the structure should have a very tolerance with the process damage, so that wastage can be minimized and it is more economical also. So there are different ways that we can make these 2D layered materials or thin films, which is actually different kinds of sputtering, as I already explained to you, the reactive sputtering, magnetron sputtering, ion beam or cluster beam sputtering. And if you wanted to have a single crystalline films, this sophisticated technique has to be adopted, like MOCVD, metal organic chemical deposition, or MBE, molecular beam epitaxy, or LPE, liquid phase epitaxy, or vapor phase epitaxy. So depending upon the the availability of raw materials and also requirement, you can go for different kinds of epitaxial technique. And the PLD, as I said, is a versatile technique to go for, suitable for high temperature oxide materials. And the sol gel method is the very inexpensive method, which is very conveniently started with any laboratory, provided you have the high purity chemicals available for the synthesis. So let us start from this sol gel synthesis, as I said, because this is the easiest way. And the sol gel synthesis involves molecular mixing of the solutes or the raw materials in the solvent. And this molecular mixing ensures a very high purity, and high purity also Apart from this high purity, we can also control the chemical homogeneity of the structure. And if you go for multinary structures like binary to ternary, ternary to quaternary, it was possible we can control the stoichiometry very perfectly. And of course, the large area deposition, which is also useful for technological application, can also be realized. And we can prepare the bulk material, 3D material from this solvent synthesis. And this material can be converted into 2D form by spin coating, or we can do dip coating, or we can go for a spray coating also. Okay, so I'll just have some demonstration about it. This is the simple protocol for solvent synthesis. You take the salt, mix with the material, then you convert them as the gel. And this gel is basically two different kinds of gel. One is the aerogel, if you have the air gap in between the molecular structure. And if you have the dense molecular structure, this becomes zero gel. Right? The aerogel is useful for storage applications because it will have a large porosity. And then zero gel is the very dense structures where we can make the dense films like this, or we can also use it for dense ceramics, which is useful for cutting tools and other applications. So once you prepare the salt, this is actually the video. As I said, it doesn't need much sophistication. What you need is a small mechanism for stirring the solution to make the uniformity. Then you have the glass, vessels or beakers. Then you have to have the raw material for this. Okay, so once you prepare the material, then it can be coated on a substrate by spin coating process. And the spin coating process involves that you take this salt and then just allow to deposit on the fall on the substrate, and the substrate is attached with this sample holder. It just rotates at the very high speed of about 3000 to 4000 RPM, and the liquid falling on the surface gets uniformly dispersed over the entire area of the substrate. Then you have the uniform coating. And this spin coating is useful for very uniform coating on flat surfaces. And if your substrate is not flat enough, then it will be difficult to have the uniform coating on there. And after the coating, that solvent can be volatile, which can evaporate. Then you get the material deposit on that. So this is actually the demonstration. You have the substrate over which you just pour the salt, and then it is just allowed to rotate at a very high speed. It goes to 3000 RPM, and after the deposition, you can just take, this is the substrate, you can just take the substrate. You see that coating is done on the substrate. Okay, so this is also not a very expensive technique, and the spin coating unit costs about 1.5 to 2 lakh, very automatic controlled spin coating, which can go up to 3000 RPM. And the substrate, you can use a glass substrate or semiconductor, any kind of substrate based on the requirement. So another technique is that you can do the spray coating. The advantage of spray coating is they take the material in a spray gun and introduce the compressed air so that it gets out of the nozzle and then it gets deposited over the substrate. And you have the mechanism to heat the substrate so that the wetting and homogeneity can be achieved perfectly. And of course, we have different kinds of peripheral devices for that. This spray coating technique is a very powerful technique for a wide range of applications, especially high purity, chemically homogeneous thin films. And you can use any kind of substrate because the substrate heating is very minimal heating. It can go 300 to 350 degrees Celsius. Some of the glass substrates can also be used, or any kind of oxide substrates can be used. And this is the demo where you take the salt in the spray gun, and this is the substrate. You just move across the substrate and you get the uniform coating of that. Okay, your substrate heating mechanism is here, and this is the thermocouple to sense the temperature, and you can optimize the process. So this is the automatic deposition of the spray pyrolysis unit. And the other techniques which I told you about, the PLD. PLD is actually a little sophisticated technique where you have to have the high energy laser beam with very high power, and then the chamber itself is a high vacuum chamber which can, the typical pressure is of the order of 10⁻⁻6 to 10⁻⁷ torque. and you have the sample holder here, then the target is fixed here, you have the laser beam hitting on the surface, then plasma is produced, the plasma carries the atoms towards the substrate, and then substrate heating is attached here, then you have the coating of this film. Okay, so this is the typical PLD chamber, and these are the parameters to be optimized. And so the mechanism is the moment laser hits on this target, then there is a very small thickness of the surface melting, and this surface melting induces the vaporization followed by multiphonon ionization, which produces the plasma. Then the plasma carries the ions towards the substrate. So the entire process is done within a very fast, within a very quick of 1 to 30 nanoseconds. So you can just see the the speed with which the process happens. So this is actually the way the atoms are ejected from the substrate. It goes from the target, it goes towards the substrate and get deposited over the substrate. And this is actually the plasma produced for a barium titanate sample in a vacuum chamber. And this can be controlled by controlling the laser beam at temperature or the laser power, everything, so that optimization can be done. And this is the MOCVD technique. As I said, the metal organic chemical deposition means that raw material should be in the organometallic form. And this is a laboratory scale, very nominal reactor. And the cost of this reactor is about 5 crore now. Okay, so the raw materials are taken in this chamber, and then, for example, if you wanted to have gallium arsenide, that arsenic is the vapor, it is taken in the cylinders, and gallium is basically the metallic gallium, liquid metal. But here we cannot use the liquid metal because it evaporates at 4 degrees Celsius. So therefore, we take the organometallic form of gallium, which is trimethyl gallium. So trimethyl gallium and arsenic, which are taken in this source chamber, then it goes through these stainless steel tubes, and this is the deposition chamber, and this is the loading chamber. Your substrate is loaded here, then you control all the process through this fume cupboard, and then it just introduces the substrate here. Then you have the source coming here, and it gets deposited. After the deposition, the residues are taken through this exhaust, and this is directly fed through this kind of scrubbers, and these scrubbers are the scrubbers purify the toxic gases, and then it gets let it to open atmosphere. So this is actually very simple, very small scale reactor, which is about 5 to 6 crore cost. But if you want to go for large area deposition for the industrial scale, then obviously the scaling up will be very high, and the industrial scale reactors cost about 15 to 20 crore. So this is actually the mechanism, because there are a lot of complicated structure which is there, and these are the raw materials taken in the chamber, and then it goes through the tube and then goes to the substrate. Then we have the heat shunt and other vacuum pump, everything is there. Okay. So the next is about the atomic layer deposition. Atomic layer deposition is also a sophisticated process where you take the material, and then the advantage of this one is that the vacuum chamber is integrated with the different kinds of detectors, so that the in situ observation or the in situ characterization can be done in the atomic layer deposition. And there are four different steps in this kind of category. For example, the first step is that you supply the precursor from the source, and then it goes, and then we have the purging the substrate to have the surface cleaning, and then you have the source which is just deposited over the things, and then it can also be peeled up using the plasma, and then you get the structure over that. So this is where that the schematically the atomic layer deposition works. And there is a very sophisticated technique where, because I said, the deposition can be done by atom deposition. Then we can have a very controlled growth and The growth can be lateral or it can also be vertical depending upon the configuration of this chamber system. This is what we have the deposition happening in the So this is what we have the deposition, and for example, in every stage, this can be controlled by controlling the vacuum or controlling the pressure or controlling the temperature or controlling the feed of the source towards the chamber. And these are all sophisticated technique, and there are some technique which are all very convenient also. We don't have to go over a sophisticated technique to make these 2D layered materials. One is the thermal evaporation. As I told you, this is the typical thermal evaporation system, which is attached with the magnetron sputtering. And this is actually, you have the material taken in a container, and if you just heat it with the resistive heating, or you can also use the electron beam to just heat the material and decomposes and then evaporated, and then evaporation goes there. Then you have the collector here, which is a substrate, and everything is done in a vacuum chamber. And we can use the resistive heating, or we can also go for electron beam based on the requirement. And there are some very simple coating techniques also available. These coating techniques are useful for coating metallic surfaces, metallic coating on the bulk material. Normally, when you have electron microscope, whether a scanning electron microscope or TEM, transmission electron microscope, so you have, for example, you are going to use insulating material. In order to control the charge effect, you have to have a metallic coating on that. And this kind of simple coating is around 2 to 3 lakh rupees. And these kind of things cost, if you have a magnetron sputtering, this costs about 12 to 15 lakh. Okay. So still there are some simple techniques where we can make the 2D layers, which is about the chemical bath deposition, where you take the material in a glass beaker or chamber, and then introduce a sample holder, and this is the ITO coated glass substrate which is introduced on there. Then you have the hot plate just to have the homogeneity of the solution. And to control the pH, you have the pH probe, or control the temperature, you have the temperature probe. And so everything can be covered with a evaporation controlled seal. And then you induce the deposition on the substrate. And the typical temperature is around 85 to 90 degrees Celsius. But this is a very fast process, because as long as you maintain the homogeneity, and within 20 minutes, we can just get the deposition of around 80 to 100 nanometer on a substrate like this. So these are the different methods which are all used for the 2D layers. And I'll just take 2 minutes about the graphene. As I told you, graphene is the very interesting material. There are different kinds of methods available, because there is not a very single or designated technique for graphene synthesis. We have a variety of methods available, like mechanical exfoliation, thermal exfoliation, liquid exfoliation, chemical reduction, chemical vapor deposition, solvothermal, hydrothermal, microwave. Any of these methods can be used. And the speciality of this material is based on the application, you can choose your own choice. For example, if you want to use it for sensor applications, we have to obviously go for liquid phase exfoliation. If you wanted to use it for flexible devices, we can go by CVD. Or if you want to use it for supercapacitors, energy storage, or solar cells, we can go by chemical reduction process. Or for biomedical applications, we can go by CVD. Or if you wanted to use it for EMI shielding or high strength material of this graphene, we can go by chemical reduction process. So therefore, the choice is what for we are making this material. Accordingly, we can choose this technique. I'll just give, because among all these techniques, the chemical reduction is the simplest method to make this graphene. So what we do is we take the natural graphite is the raw material, and then mix with very strong acids just to isolate the layer structure of these graphitic layers, and then introduce the oxygen functional groups by deliberately oxidizing, introducing the oxidizing agent. Then you have the oxygen functional groups introduced in that. Then just to filter it, wash it, and then dry it at a vacuum, then you get the graphene oxide. So now you have the graphene oxide enriched with oxygen functional groups. So now you wanted to reduce this graphene oxide to convert it into graphene. So this is done by sonication process. You take graphene oxide, mix with water, sonicate it for about 1 hour, you get graphene oxide dispersion. From the dispersion, you use any of the reducing agent. Here we have used thiourea as the reducing agent. Reflects it at 95 degrees Celsius for 12 hours, you get what is called reduced graphene oxide. So, if you are able to reduce all the oxygen functional group, there will be different kinds of oxygen functional group like carboxyl, hydroxyl, carbonyl, and epoxyl groups. And if you are able to get rid of all the oxygen functional groups, then we get what is called a graphene. But the chemical reduction process, sometimes there will be a residual oxygen functional group still present in the matrix. Therefore, we safely called as reduced graphene oxide. Okay, so this is the simplest way of making this graphene oxide or reduced graphene oxide. And if you are successful, you can also make it graphene out of this. But in the case of composites, when we wanted to make the composite structures, the best way would be to go for solvothermal synthesis. Solvothermal is nothing but hydrothermal if you use organic solvents. And this is actually called as an autoclave. And the autoclave is made up of stainless steel, and then you have the mechanism to introduce the solution, and then you just seal it with the stainless steel lid. And the temperature is around 300 to 400 degrees Celsius. The pressure can be around 10 power minus 3 torr with this kind of thing. So the parameters to be optimized in this solvothermal method is the reaction temperature, reaction time, selection of solvent, surfactant if necessary to go for zero-dimensional materials, and also the precursor type, whether it's organic or inorganic or organometallic kind of thing. So, this advantage of this solvothermal method is it can be used for a variety of material like zero-dimensional, one-dimensional, two-dimensional. We can use it for three-dimensional structures also. So then we'll move on to the three-dimensional bulk nanomaterial. I'll take another 5 minutes. This is actually the you take the material in a solid form, whether it's a micron size or a few millimeter size, then introduced with this kind of metallic balls. And when we this is subjected to cylinder, grinding for a few hours, these materials will have undergo a very severe plastic deformation, and this plastic deformation reduces the size of this particle. And so this mechanism is used to make these nanoparticles, and the particle size of around 50 nanometer can be conveniently synthesized by this ball milling process. And this is the typical small scale ball milling. It costs about 2.5 to 3 lakh rupees. And of course, high power ball milling is also there, where we can bring down the size even less than 20 to 25 nanometer. Okay. And this is about the micro synthesis. As I said, the micro synthesis is a very efficient way of making bulk materials. As I said, the microwave energy can be absorbed by the material through ionic conduction and also dipole rotation. So there is an instant heating possible because of this mechanism. And the microwave is a high power radiation with the frequency with the gigahertz range. So instantly it can be heated. And this is the advantage. For example, if you take a conventional heating for a material, it takes typically around 10 hours like that. And the same process can be completed within 2 hours or within 1 hour by using the microwave synthesis process. So in addition to that, the surface uniformity or uniform particle size can be achieved by microwave sintering. This is the microwave sintering compared to conventional sintering, but the uniformity is very, very poor. And also the lattice strain for this conventional synthesis material is very high, and the microwave sintered materials will have very low strain. And there are some requirements, very specific requirement. For example, if you take zirconia toughened alumina, this is a high temperature material useful for reactive coatings at high temperature. So at room temperature, for example, if you take aluminum oxide and zirconium oxide, both are in the tetragonal structure. But when you heat it at 750 degrees Celsius, the zirconium oxide undergoes monoclinic phase transformation, but Al2O3 is still in the tetragonal space. So because of this phase transformation, there is a severe strain induced in the lattice, and you can just see some kind of macroscopic defects or voids which is observed. And this kind of structures are not so useful for applications. So when we go for microsynthesis, then this kind of phase transformation will not give any lattice strain. Then you will have a very uniform coating of these kind of materials. That is what the advantage of this microsynthesis. And you can just see the zirconia upon alumina, where you have the uniformity in the conventional method. And if you look into the crystallinity is only the second order crystallinity is achieved for conventional sintering, whereas micro sintering you have at least fifth order crystallinity is achieved, because the crystalline size, the perfection of this material is very high compared to the conventional sintering methods. And the last one is about the biosynthesis, and biosynthesis is a very convenient way. Advantage is that it is very inexpensive. We have a lot of herbals which is very rich in minerals and metals, and those kind of minerals and metals can be prepared from the plant extracts, and the raw materials are easily available. And of course, to some extent, it is non-toxic because we don't use any synthetic chemicals as the raw materials. But sometimes we use the catalytic to induce the reaction. We use the synthetic chemicals. So this is actually the plant extract, and plant extract contains a lot of photochemicals, and these photochemicals, but alkaloids or polyphenols, these are all basically very strong reducing agents, and these reducing agents reduces the metal ions into the neutral metal ions, and then it induces the nucleation at the level, then you get the metallic nanoparticles. So this is actually the typical example how the silver nanoparticles are prepared from the fenugreek extract. So we just take the fenugreek and then chop it and then boil it at 95 degrees Celsius for 5 minutes. Then you have the extract. And here we use the catalytic solution, silver nitrate solution. Then this used for colloidal solutions, and just grind it and then dry it. You have the silver nitrate particles. There are some techniques even without using this catalytic reaction. If we just do it for a very longer hours, it was still possible that we can get a small amount of silver nitrate particles, and those techniques are called very green synthesis methods. But in order to have the faster reaction, if you use the synthetic chemicals, then the biosynthesis becomes very economic. Then we can also use it for not only for silver, we can use any kind of noble metals like gold or platinum or palladium. Of course, we have to go for different sources like neems or different kind of leaf extract to prepare the metallic nanostructures. So I think more or less we have covered all the techniques. There are some very specific requirements where we go for non-aqueous synthesis, which is especially for oxide materials like cerium oxide or zinc oxide kind of thing. Finally, I'll just introduce you what we have been doing at our Nano Center. We work on different variety of materials, starting from 3-dimensional bulk, 2-dimensional nanostructures, 1-dimensional nanotubes and nanofibers. Then we also have biosynthesis and some specific techniques. And these are all the facilities available in our laboratory, and the material synthesis and processing facilities. These are all material characterization facilities. So if any of you wish to use some of our facilities, of course, after this lockdown, then you are most welcome to write to us. Then you can make use of this one for your projects or your students' projects. So I think with this, I'll end my talk, and thank you very much for all of you. And I'm sorry that I have taken a little more time because there was a delay in the initial stages. Okay, I'm done now, and I'm happy if you have any questions or clarifications to be answered. Okay. Thank you, Dr. Pari. Hello?
Thank you, sir. Thank you, sir.
Yeah.
Kumariswamy.
Sir?
Kumariswamy. Hari, proceed. Hari.
Yeah.
Hello.
Just ask whether participants have any questions
Yes, sir.
or clarifications. Nobody is there?
Vanji.
Hello, good
Yes,
afternoon,
sir.
Yeah.
Yeah, I'm Bipin John from Christ Deemed to be University. So my first of all, your presentation is excellent and it's very informative. My
Can you be
doubt
little
is
loud, please? Because we are not able to hear you.
okay. So your presentation is excellent and very informative. My doubt is regarding you mentioned that in grinding, during grinding, I mean ball milling, the material will undergo hard plastic deformation. If the particles have plastic deformation, that will affect the physical and all the properties like optical properties and electrical properties. Then how we can use that nanoparticle for the application, especially optoelectronic application?
Actually, the plastic deformation is only to reduce the size of these particles. Okay, so for example, if your raw material is very pure without any impurities, then there will not be any impurity added through this because the balls making is made up of high strength metallic like tungsten balls or inconel balls. So there will not be any impurity added to the material from the metallic surface. Only thing is it is subjected to severe plastic deformation. Plastic deformation will not change the physical property of the material. It only reduces the size.
Okay.
So
that even change the structure also. It will not affect the structure. I mean the crystal structure.
Yeah. So only reduce the particle size.
Okay. Thank you, sir. Okay.
Sir, I have one question.
Yeah.
Good afternoon, sir.
Yeah. Good afternoon.
Sir, participants have posted some questions in the chat box. So I'm going to read one by one, sir. Can you answer, sir?
Sure.
Size reduction means band gap will be increases. How the conductivity of graphene oxide increases?
No. Actually, the graphene basically the size reduction, the size increase with the reduction in the band gap is only for quantum dots.
Yes.
Okay.
Sir.
Yeah, if you make a graphene quantum dot, that was not possible with the graphene, but it's also possible that we can make the graphene quantum dots. But generally, if you take a 2D graphene is a zero-dimensional, zero band gap material. There will be a overlapping of valency band and conduction band. Okay?
Yes, sir.
There are a lot of good amount of theoretical concepts on that. Because the Dirac point, the point where there will be overlapping of valency band and conduction band, and because of this overlapping, then it has extreme conductivity.
Yes, sir.
So the
another
variation in the size with the energy gap is only applicable to the zero-dimensional nanoparticles, that is quantum dot particles, where the energy levels will be very discrete between the valence band and conduction band. So that discrete energy levels becomes more stable when we change the size of these particles.
Okay, sir. Another question from Dinesh Babu.
Yeah.
So what is the use of thermogravimetric analysis in nanocomposites? What we can able to find with that?
So actually, in the nanocomposites, you can just see the nanocomposite is basically made up of more than one compounds, right? So if its melting point is very different, then you can find out the decomposition of this individual material or the melting point of the material, or if it can have some kind of oxygen evolution, if it is oxide, or if it is a kind of sulfides goes to some kind of volatile nature. So those kind of reactions can be very clearly observed in the thermogravimetric analysis. Main thing is the melting point or the dissociation temperature, decomposition, or the reaction is exothermic or endothermic. So all these kinetics can be studied using the thermogravimetric analysis.
Okay, sir. Thank you, sir. Another one question from Radhika Deshmukh. Astrophysics and nanotechnology, how can we reconnect?
Astrophysics is something entirely different. But nano is a dimensionality. So for example, if you take in atmosphere, there are some kind of nanoparticles. The dust particles are nano size, maybe. That is what we can connect. There is no absolute physical connectivity between these two.
Yes.
Okay.
Okay. One more question, sir, from Dr. Anish Rajan.
Yeah.
Chemical precipitation method and colloidal synthesis belongs to what kind of approach? Top-down or bottom-up approach?
This is actually colloidal synthesis is actually bottom-up approach. Chemical reduction or chemical precipitation, right?
Yes. Yes,
Yeah.
sir.
Yeah, chemical precipitation is actually the top-down approach, because we are taking the raw material, but once it is dissolved, then it goes to the atomic size. From the atomic size, then we build the 3D by precipitation process, 3D or 2D like that. Okay.
Yes, okay, sir. Okay, sir.
Yeah.
So another question from Sudhir: how the hydrothermal method is different from solvothermal method?
Yeah, that I told you, no, because the experimental configuration is very same. The solvent, if you are using water, then it's called hydrothermal. If you use any organic solution, it becomes solvothermal. That's it. That is the difference.
Yes. Okay, sir.
The use of the choice of the solvent.
Yes, sir. Yes, sir. I think no more question in the chat box, sir.
So thank you. Then we'll end up, and I once again thank all the participants, because it's almost 2 hours now. Okay.
Yes, sir. Thank you, sir.
Just a minute, sir. Just a minute.
So now, yes, sir. The conversation.
Yeah. Good afternoon to all. As we come to the close of this national webinar program on preparation methods and deposition techniques of nanostructure, the best and beautiful things in the world cannot be seen or even touched. They must be felt by heart. Thank you in one such prayer among them. Today, my words are not enough to express my gratitude. It's my great pleasure to deliver the word of thanks. First of all, I would like to propose the hearty vote of thanks to our distinguished guest, resource person, Dr. R. Jayavel, sir, Professor, Director, Center for Nanoscience and Technology, Anna University, Chennai, for excellent presentation and made this seminar more interesting and innovative one. Friends, we know that no program can become a successful with a single person, but our resource person is different. Because of he himself only, this webinar program a great success. So thanks a lot, sir. The man behind the success is purely all the credit goes to you, sir. Thank you very much. On behalf of our college management and physics department staff members, we extend our sincere thanks for our resource person, Jayavel sir, who spared the time from his busiest schedule to grace this occasion. Thank you very much, sir. I would like to express our profound gratitude to our principal, Dr. R. Sundararaman, for his presence and moral support. Thank you, sir. I would like to thank our beloved head of the department and coordinator of this program, Dr. S. Hari, because event like this cannot be happen overnight. The wheels start rolling more than a month ago. It requires planning and a bird's eye for detail. Thank you very much for our HOD to provide such a thought-provoking webinar program. Thank you, sir. I also extend thanks to the team members who have been running around doing a lot of things, especially Kumaresh Sowanji, TVS sir, Hariharan, and others. Thank you very much, my dear friends. I would like to thank this opportunity to place on record our hearty thanks to our physics department staff members for their dedication and enormous help, especially for their cooperation. Finally, the participants who have turned up in such a great numbers, not only from our physics department, but also from various departments, various institutions, and various industries, and also various places. So they spend valuable time with us. Thank you, one and all. Again, I once again thank you for the participants. Please be safe, stay at home. Thank you very much.
Thank you, sir.
Thank you. Congratulations, Pari.
Thank you, sir. Thank you, sir.
Okay.
Thank you, sir.
Yeah, there was a call and from the office. Okay.
Yes, sir. Yes, sir. Thank you, sir. Yes, sir. Thank you, sir. Thank you. Sir. Thank you.
Thank you, Prof.
Hariharan, thank you. TVS, Ilandran, Kumarasu sir. Thank you.
Thank you, sir.
Thank you.